All right, let's talk about a name I guarantee you know from math class, Pythagoras. Now, you're probably thinking a squared plus b squared equals c squared. And yeah, you're right. But what if I told you that little formula is just the very, very tip of the iceberg? Today, we're going to pull back the curtain and see the truly beautiful and powerful idea hiding right underneath.
So here's what we've got lined up. First, we'll look at why it's more than just a formula. Then, we'll put it into practice. After that, things get really interesting. We'll take it off the page and into 3D space. Then, we'll flip it around and use it like a detective. And finally, we'll uncover its secret power. Seriously, you're going to want to stick around for that last one. It's a game changer.
Okay, let's kick things off with section 1, more than a formula. It's time to completely reframe how we think about this whole a squared plus b squared equals c squared thing.
So let's just get right to it. When you see that equation, what is it actually saying? I promise you, it's about something way more visual and intuitive than just finding the side of a triangle.
And here it is. This is the big aha moment. The theorem isn't really about the lengths of the sides. It's about the areas of the squares you can build on those sides. Just look at this. The area of those two smaller squares, if you could somehow melt them down and pour them into the bigger one, would fit perfectly. That's the real idea.
So to put it officially, this is what Pythagoras' theorem is all about. The formula is just a handy algebraic shortcut. What's really happening is this beautiful geometric truth. The area of the big square equals the sum of the areas of the two smaller ones. Simple as that.
All right, theory's great, but let's get our hands dirty. Welcome to Section 2, the theorem in action. Think of this as a quick boot camp to make sure we've got the basics down cold. Okay, first up, a total classic. You've got a right-angle triangle. The two shorter sides are 3 units and 4 units. The mission, should you choose to accept it, is to find the length of that long side, the hypotenuse c. So first step, we just plug what we know into our trusty formula. That gives us 3 squared plus 4 squared equals c squared. Let's do the math. 3 squared is 9, 4 squared is 16. Add them together, you get 25. So the area of that big square on side C is 25.
And of course, the square root of 25 is 5. And there you have it, the famous 3, 4, 5 triangle. It's one of the classic Pythagorean triples, these really neat triangles where all 3 sides are perfect whole numbers. So satisfying.
Okay, ready for a little twist? Let's flip it. This time, we know the longest side is 13, and one of the short sides is 5. We need to figure out the length of that missing side, y.
It's the same idea, we just have to rearrange the formula a little bit. If the two small squares add up to the big one, then the big one minus a small one must equal the other small one, right? So it's 13 squared minus 5 squared.
And when you run the numbers, 169 minus 25 is 144, and the square root of 144 is 12. And check that out, another perfect Pythagorean triple, 5, 12, 13. Pretty cool.
All right, we've nailed it on a flat piece of paper. Now for the really fun part. Section 3 is all about taking this rule off the page and launching it into the world around us. We are entering the third dimension. So check out this challenge. We need to find the length of that line running straight through the guts of this box, from the front bottom corner to the back top corner. At first glance, you might think, how on earth does Pythagoras help me here? Well, the secret is to see the hidden triangles. You can solve this whole thing by just using the Pythagorean theorem twice. First, you use it on the floor of the box to find the diagonal of the base. Then, that diagonal becomes the bottom of a new triangle that stands straight up inside the box. It's brilliant. So let's say the box's sides were 3, 4, and 12. We'd find the diagonal of the 3 by 4 base, which we already know is 5. Then that 5 becomes the base of a new triangle with a height of 12. You run Pythagoras one more time and you get 13. It's a perfect example of how you can stack a simple 2D rule to solve complex 3D problems. Okay, time for a total paradigm shift. Up until now, we've always assumed we had a right angle, and we used the theorem to find a length. In this next section, we're going to use it backwards, like a detective, to figure out if a right angle even exists in the first place.
This really breaks down the difference. Before, finding a length was all about solving for A, B, or C. Now, verifying an angle is about checking if the two sides of the equation are actually equal. We're not solving for anything, we're testing a hypothesis.
So here's our crime scene. We've got 3 points on a grid.
And, it kind of looks like there might be a right angle down there at corner C. But in math, kind of doesn't cut it. We need proof. And Pythagoras is our forensics kit.
First thing we do is figure out the squared length of each side. And the cool part is we don't even need to find the actual lengths yet, just their squares, which is exactly what the formula uses. So we gather our evidence. The squared lengths are 5, 20, and 37.
And now the moment of truth. Do the two smaller squares add up to the big one? We check. 20 plus 5 is 25. But the square of our longest side was 37, and 25 does not equal 37, not even close. So, case closed. This is not a right-angled triangle.
Okay, this is it. We've arrived at the grand finale. We're about to uncover the theorem's real secret power, and I promise, this is the part that will totally change how you see it forever.
So after everything we've been through, I have one last very important question. We started with the idea that this is all about the area of squares on the sides of a triangle. But does it have to be squares?
And the answer, which is just absolutely amazing, is no. It doesn't have to be squares at all. The theorem works for any set of similar shapes. Just look at this. The area of the two little semicircles on the short sides adds up perfectly to the area of the big one on the hypotenuse. It could be hexagons or little stars or anything you can imagine, as long as the three shapes are proportional.
And this right here is our final takeaway. This is the ultimate generalized truth of the theorem. The squares we learned about are just one simple example of this incredible universal rule. The area of the figure on the long side is equal to the sum of the areas of the figures on the two shorter sides. And that is the true secret power of Pythagoras' theorem.